for hundreds of years. We believed the depths of the universe were empty. The most powerful telescopes looked. They saw only pitch-black darkness. But in 1995, everything changed because we were catastrophically wrong. The Hubble Space Telescope locked onto the emptiest spot in the sky for 10 straight days, and from that nothingness, a full 3,000 galaxies erupted. Some were 12 billion years old, so, according to cosmological models, they shouldn't have formed yet. But that wasn't the most unbelievable part. These galaxies called into question everything we knew about the birth of the universe. So how did they do it? If you too are curious about how one of the universe's greatest mysteries was solved, then like this video and join the channel. Because your perception of the cosmos is about to change forever, let's begin. We believed the depths of the universe were largely empty. We thought of the cosmos as a vast canvas. But on this canvas, there were only sparsely scattered galaxies. The rest was cold, dark, and absolute nothingness. This was the standard view in the world of astronomy until the year 1995. Yet, in December of that year, a daring experiment would fundamentally shatter everything we knew. Because a group of scientists deliberately pointed humanity's most powerful telescope at nothing. And what they saw changed our view of the universe forever. At the heart of this audacious decision lay a concept: observable nothingness. What does this mean? Astronomers had identified a special spot in the sky near the Big Dipper constellation. Its exact coordinates were right ascension, 12 hours, 36 minutes, 49.4 seconds, Hawk, and declination plus 62 degrees, 12 minutes, 58 seconds. This point was the clearest window in the sky, because the interstellar dust of the Milky Way was very thin there. It was like a perfect peephole to view outer space. But even when viewed with the most powerful telescopes on Earth, the only thing visible there was pitch-black darkness. Robert Williams, who was the director of the Space Telescope Science Institute at the time, decided to place a bet on this very nothingness. He would dedicate a full 10 days of the Hubble Space Telescope's valuable observation time to this void. This was more difficult than trying to find a single candle flame kilometers away in a pitch-black ocean. This decision split the scientific community in two, but because this was much more than just curiosity. This was a test of a deep-seated belief about what the universe held in store for us. To understand why this gamble was so controversial, we need to know the dark paradigm of that era. The prevailing view at the time was that the universe had a very sparse structure. Astronomers believed that once they reached the faintest level of brightness that telescopes could detect, the limiting magnitude, there would be nothing else to see. This was like assuming that after a certain depth, there would be no more fish in the ocean. Even the Hubble Space Telescope was designed to observe celestial bodies above a certain brightness. But Williams and his team wanted to push these design limits to their absolute breaking point. Their goal was to achieve something that was difficult even to imagine. They wanted to capture the faintest photons that had traveled for 12 billion years, resisting the expansion of space to reach us. These particles of light came from a time when the Earth or the solar system did not exist. Therefore, this mission was not a simple photo shoot. It was an effort to raise the antenna to its highest point, to hear the faint whisper that the universe had sent before humanity even existed. A scientific dogma was about to be broken. But no one knew what they would encounter. If Williams was wrong, millions of dollars worth of observation time would be wasted. But if he was right, our knowledge of the universe would be rewritten. This is why this 10-day observation, known as the Hubble Deep Field Project, YASH, or HDF, became one of the most important turning points in modern scientific history. The area the telescope looked at was incredibly small. It was only 1/30th of the area covered by the full moon in the sky. This was a region as small as a grain of sand held at arm's length on your fingernail. But the data that seeped in through that tiny opening created a massive shockwave. At that point, believed to be pitch black, there were more than 3,000 galaxies, glittering like jewels. Each one contained hundreds of billions of stars. This discovery proved two things about the structure of the universe simultaneously. First, it confirmed the cosmological principle, meaning the universe, when viewed on a large enough scale, is the same and homogeneous in every direction. Second, and more importantly, it slapped us in the face with how shallow our knowledge of the universe was. The place we thought was empty was actually one of the most crowded and bustling neighborhoods in the universe. The galaxies of the early universe were not like today's elegant spiral or elliptical galaxies. They were irregular and chaotic structures that were constantly colliding, merging, and breaking apart. This was the moment humanity looked directly into the childhood of the universe for the first time. This discovery was proof of how vast and dense a history the universe possesses. Where we thought there was nothing, there were thousands of galaxies. But, ya Fadil, each of these galaxies held new mysteries within itself, because this 10-day observation made us question not only what existed, but also why it existed in that way. This chaotic landscape showed us the violent and creative process at the very beginning of evolution. So why were these galaxies so different from what we knew? Why did they appear so irregular and fragmented? And most importantly, what was it that packed so many galaxies into such a small area? What made this shocking view possible was much more than a simple photograph. It was a feat of unprecedented technical precision that pushed Hubble's own limits. And it necessitated the implementation of the most sensitive observation protocol modern science could achieve. Because this wasn't just about pointing a telescope in one direction and waiting. It was a struggle to keep a massive machine orbiting the Earth at 27,000 kilometers per hour, fixed on a single point for 10 days without a millimeter of deviation. The first step in this impossible mission was for Hubble to overcome itself. To do this, scientists resorted to a trick they called the Continuous Viewing Zone, or CVZ. Hubble orbits the Earth at an altitude of about 547 kilometers. Therefore, for about half of its orbit, it is blinded by either the Earth's shadow or the sun's glare. But there are special regions near the celestial poles. Here, the Earth never blocks the telescope's line of sight. It was within this CVZ that Williams and his team found that perfect window, where the dust from the Milky Way was at its thinnest. Yet, the light coming from this window was unimaginably faint. They had to capture light that was billions of times fainter than the dimmest star we can see at night. So, they looked at the same spot over and over for 10 days, conducting a total of 342 separate exposures. This was like shooting short films, each lasting 15 to 45 minutes, and then combining them all. Because exposing for such a long time brought out another major enemy, cosmic noise. The hero of this epic observation was Hubble's heart. The Wide Field and Planetary Camera, 2 Mustahacha, or WFP-C2. This camera was not a simple recording device. It was the most sensitive digital eye humanity had produced at the time. It consisted of 4 separate CCD sensors. While 3 of these sensors scanned a wide area, one focused on the center with higher resolution. This is why the resulting images had that iconic L-shaped stepped structure. But the real magic was in the filters used. The research team used 4 different spectral filters: ultraviolet, F300W, blue, F450W, visible light, F606W, and near-infrared, F814W. So why were 4 different colors necessary? Because, the universe was expanding. An ultraviolet light wave that sets off from a very distant galaxy gets stretched by the expansion of space during its billion-year journey. Therefore, by the time it reaches us, its wavelength has lengthened, shifting it to red, or even infrared. We call this phenomenon redshift. By comparing the brightness in these 4 different filters, scientists could analyze the color of the galaxies. This gave them a kind of cosmic ruler with which they could measure how far away, and therefore how old and bold each galaxy was. But using this cosmic ruler was not easy at all, because not every signal that reached Hubble's sensors came from a galaxy 12 billion years ago. The biggest enemy was cosmic rays. These invisible, high-energy particles from the Sun or outside our galaxy struck the CCD sensors like bullets. Each impact left a bright white dot or streak in the image. These false signals were many times brighter than even the faintest galaxies. It was impossible to analyze the data without cleaning up this noise. This is where an ingenious technique called dithering came into play. For each of the 342 exposures, Hubble intentionally shifted its aim by a tiny amount, smaller than the size of a single pixel. This ensured that real celestial objects remained in the same place in every photo, while random noise like cosmic rays appeared in different positions. By stacking hundreds of photos, the scientists mathematically erased everything that was not common to all frames. That is, all the noise. This was like stacking hundreds of transparent films and revealing the common picture while filtering out the dust specks on each individual film. As a result, this 10-day process went far beyond a simple observation. A perfect orbital dynamic was calculated to look into that void. Special filters were chosen to measure the age of light, and brilliant algorithms were developed to clean the incoming data. The 342 raw images, which looked like meaningless piles of noise when viewed individually, were now ready to be assembled. Humanity was about to face a sight it had never seen before. So, what would the final image reveal when these meticulously processed data were combined? What exactly were the shocking findings that stunned astronomers, and how would these findings, how would they change the most fundamental theories about the history of the universe? No one could have predicted it. Because when hundreds of raw images were meticulously combined and that single, final frame emerged, the scientific world literally held its breath. The curtain that was supposed to be pitch black had been lifted, and what stood behind it, was a shockwave. Here are the findings. The first shock was the numbers themselves. There should have been nothing there. But there was. Thousands of them. More than 3,000 separate points of light. And each one wasn't a single star. Each one was a massive galaxy containing hundreds of billions of stars. This was an incredible density. The observed area was as small as a grain of sand in the sky. If there were this many galaxies everywhere in the universe, a simple calculation meant there had to be at least 200 billion galaxies in the observable universe. This was more than 10 times the estimates of the time. The cosmological principle, the theory that the universe looks similar in all directions, was shockingly proven by this discovery. But this proof did not bring relief. It brought vertigo. Because it showed that the universe was far more crowded, far richer than we had ever imagined. The place that was supposed to be nothing was actually like a metropolis. Scientists were stunned. The models had not predicted the universe to be this full. This discovery changed the question from how big is the universe to how full is the universe. But that wasn't the real shock. It wasn't just the number of galaxies, but their shapes that were impossible. The galaxies we know are elegant, majestic spirals like Andromeda, or orderly elliptical structures. They are like the mature, Schlag-Sicht calm adults of the universe. But the galaxies in the Hubble Deep Field were not like that. They were monsters. They were shapeless. They were fragmented. These structures, White described as clumpy, resembled a train wreck. These were the angry teenagers of the young universe. Because back then, the universe was much smaller. Galaxies were much closer to each other than they are today. Therefore, galaxy mergers and collisions were not the exception, but the rule. Each distorted blob in the image was actually the violent dance of systems of tens of billions of stars tearing each other apart, devouring one another. This vividly displayed one of the cornerstones of evolutionary theory, the hierarchical merging model, meaning large galaxies were formed by the gradual merging of smaller pieces over time. This discovery proved that the universe was not a calm and static place. On the contrary, the universe was a dynamic organism, constantly changing, growing, and evolving violently. And there was a reason for this chaos. Galaxies weren't just colliding. They were also burning at an incredible rate. Most of the young galaxies in the image glowed with a brilliant blue light. This blue color meant one thing: enormously hot, young, and massive stars. These galaxies were literally star factories. When scientists analyzed this data, they found the first evidence for one of the most important graphs in human history, the Madao diagram. This diagram shows how the universe's star birth rate has changed over time, and the result was shocking. Star formation was not constant. On the contrary, there was a golden age in the history of the universe, about 3 to 6 billion years after the Big Bang, in the period with a redshift value between 1 and 2. The universe went absolutely wild. During this period, one called the cosmic noon, galaxies were converting gas into stars 10 times, even 100 times faster than our Milky Way does today. The small, bright dots Hubble saw were actually fossils of that glorious era when the universe was at its most productive and brightest. This showed that the universe was once much more energetic and alive. Theories had not fully predicted such an intense burst of star formation, so how were these findings to be explained? Thousands of galaxies, chaotic shapes, exploding starbirths. All together, they pointed to one truth: the model of the universe we knew was incomplete. This was just the beginning. Because the deepest secrets in these images were hidden not just in the shapes or numbers, but in the light itself, in its wavelength. How fast were these galaxies moving away from us? And what did this speed of recession tell us about the ultimate fate of the universe? Because what this redshifted light told us was not just a story of a distant past. It was also a prophecy of the future. And this prophecy was a puzzle that made us question the most fundamental constants of the universe, time itself, and the very fabric of space. And the key to this puzzle was hidden in the phenomenon of redshift. Because the light from these galaxies told us not only of their existence, but also how fast they were receding from us. Almost every galaxy in the Hubble Deep Field was extremely redshifted. This didn't just mean they were very far away. It showed that the space between us itself was being stretched like a rubber band, elongating these light waves along the way. This was the ultimate confirmation of the Hubble-Lemaitre law. Proposed by Edwin Hubble and Georges Lemaitre in the 1920s. But the Hubble Deep Field took this law billions of light years further. The faintest, reddest dots in the image were galaxies with a redshift value exceeding 4. This meant that the wavelength of light from that galaxy had stretched 5 times by the time it reached us. This means that when we see that galaxy, we are seeing a moment when the universe was only 1/5 its present size. This discovery provided the strongest support for the Big Bang theory, because it proved that the universe was once much smaller, much denser. It was no longer a theory. It was right before our eyes. But this discovery brought with it a much deeper question. How old was the universe? The redshift data gave scientists the ability to set a clock backwards. Using the galaxy's recession speed and distance, they were able to calculate the expansion rate of the universe, the Hubble constant, with much greater precision. And these calculations determined the age of the universe to be approximately 13.8 billion years. Before the Hubble Deep Field observation, the age of the universe was estimated to be in a wide range, somewhere between 10 and 20 billion years. But the HDF data significantly narrowed this range and fixed this number, which forms the basis of modern cosmology. This is not just a number. This is our cosmic calendar. This is the birth certificate of everything that exists. Hubble told us not only how big the universe is, but also when its birthday was, and we were the descendants living 13.8 billion years after that birthday. Yet, this window opened by Hubble revealed not just a universe filled with light, but also the dominance of darkness. The distribution and movement of the galaxies in the image were much different than expected. The galaxies were moving too fast to be held together by their own mutual gravity alone. There had to be an invisible force holding these chaotic clusters together. This was one of the strongest indirect proofs for the existence of dark matter. The bright galaxies we saw were actually just the tip of the iceberg. There was an invisible gravitational skeleton holding them together. The Hubble Deep Field allowed us to map this invisible skeleton, the dark matter web. Bright galaxies were forming at the densest intersections of this dark web. This showed, for the first time so clearly, how this mysterious substance, which makes up 85% of the universe, shapes the structure of the universe. In the place where there should have been nothing, we found not only thousands of galaxies, but also the fingerprints of the true master of the universe, dark matter. When these discoveries came together, they fundamentally changed humanity's understanding of the universe. We now knew that the universe was not an empty, static, and predictable place. On the contrary, it was a dynamic, chaotic, full, and largely invisible place. The Hubble Deep Field didn't just give us answers, it inspired us to ask much bigger questions. So, how exactly did the technology used to obtain this incredible image work? How could a telescope be locked onto one point for 10 days? And how was that faint? Redshifted light extracted so clearly from a sea of noise? Because behind these discoveries lies an engineering and data processing marvel that is at least as revolutionary as the discoveries themselves. It was there all along. So, how exactly did this engineering marvel work? What were the technical secrets that made this seemingly impossible observation possible? Let's slow down the pace a bit now and take a closer look at the incredible mechanisms behind that 10-day miracle. Because the magnitude of these discoveries is hidden in the elegance of the technology that made them possible. At the heart of this operation was the ingenious use of the continuous viewing zone, or CVZ. To understand this concept, forget about Hubble for a moment and imagine yourself on a train traveling at 27,000 kilometers per hour. You need to look at a single tree outside the window continuously for 10 days. This is nearly impossible because the train is constantly moving and the scenery changes. The situation was the same for Hubble. Since it orbited the Earth every 96 minutes or so, for much of its orbit, either the Earth itself or the Sun would block its target. But astronomers found a special scenario where the train runs on a circular track, and at the center of the track is a tower that never disappears from view. That tower was the CVZ, these special regions. Near the north and south celestial poles, HOTS are never blocked by the Earth due to Hubble's orbital plane. What thus? The telescope can theoretically look at a target in these regions forever. Williams and his team conducted a months-long study to find the perfect hole within this region where the starlight and dust from our own galaxy, the Milky Way, were at a minimum. The spot they chose, right next to the Big Dipper constellation, was the emptiest-looking place in the sky. This wasn't just about looking at the right place at the right time. It was the art of finding the most perfect nothingness to look at. Without this strategic choice, most of the precious photons collected during the 10-day observation period would have been lost in the noise of our own galaxy. The second critical mechanism was Hubble's pointing accuracy, which surpassed its own limits. Finding the target was one thing, but staying on that target was something else entirely. It was like trying to shine a laser pointer into a needle's eye, kilometers away from the window of a train going 300 kilometers per hour for 10 days. To achieve this precision, Hubble uses a system called Fine Guidance Sensors, or FGS. This system uses a few bright stars in the area around the main camera, known as guide stars. As reference points, Hubble locks onto these guide stars and continuously adjusts its own position with a precision of 1,000th of a second. During the HDF observation, the telescope remained locked on its target with a deviation of only 0.007 arcseconds. This is a precision equivalent to seeing the edge of a coin from about 300 kilometers away. But even this was not enough, because the telescope itself was not perfect. Factors like temperature changes, solar wind, and even gravitational gradients cause tiny deviations in the telescope's orbit and posture. Therefore, the the control center on the ground analyzed Hubble's orbital data second by second and sent tiny correction commands to the telescope's thrusters. This 10-day operation was a flawless dance between man and machine. The brain on the ground and the eye in space worked as a single organism to capture light that was billions of years old. However, the most revolutionary technique was perhaps the one applied to the data itself: the dithering and drizzle algorithms. To understand these techniques, imagine taking a photo in very low light. In the image, you see more digital noise, random pixels, than the photo itself. This was precisely the problem Hubble faced. And on top of that, there were cosmic rays. When these high-energy particles hit the sensor, they left a bright white trail, contaminating valuable data. Dithering was developed to solve this problem. For each of the 342 separate exposures taken over 10 days, Hubble intentionally shifted its camera by 1,000th of a millimeter, a distance smaller than the size of a single pixel. What did this accomplish? Fixed celestial objects, like real galaxies, fell on a slightly different part of the sensor in each exposure. But random noises like cosmic rays appeared in a completely different place in each photo. When scientists aligned these hundreds of images on top of each other, they could mathematically identify and eliminate everything that did not appear in common across all images. That is, the noise. It was like taking hundreds of blurry photos of the same scene and creating a single clear image by cleaning the dust from each one. But the drizzle algorithm took this idea a step further. This algorithm took the pixel information from each exposure and drizzled it onto a much higher resolution virtual grid. This resulted in a final image that was much sharper and more detailed than the pixel resolution Hubble's hardware was capable of. This was overcoming the limits of hardware with software. Thanks to this technique, Hubble managed to see better than its own eye. These three basic mechanisms, strategic target selection, ultra-precise pointing, and revolutionary data processing techniques, formed the holy trinity that made the Hubble Deep Field possible. Each one was an engineering marvel in its own right. But when they came together, they created that iconic image that changed our view of the universe. Yet, these techniques did not just serve to create the image, they also formed the basis of another ingenious method that allowed us to measure the deepest secrets within that image: the age and distance of the galaxies. This method involved using light itself as a ruler, and the name of this ruler was photometric redshift. So, how could one determine that a galaxy is 12 billion light-years away using just 4 different color filters? Because behind these filters, a code that read the fingerprint left by the expansion of the universe was waiting to be deciphered. And the name of this code was the Lyman break technique, but it's better known as the disappearing galaxy trick. Because this method measures a galaxy's distance not by looking at where it appears, but by where it doesn't appear. To understand this, imagine you are looking out through a series of windows covered with different colored glass. You look through blue glass, is short, green glass, that's a copper, and red glass. If a very distant car is not visible through the blue glass, but is clearly visible through the green and red glass, this gives you an important clue about the car's color. The Lyman break technique does exactly this. In the early universe, galaxies were surrounded by a dense fog of neutral hydrogen gas. This hydrogen fog completely absorbs light below a certain wavelength, especially ultraviolet light, just like a sponge absorbs water. The exact wavelength at which this absorption occurs is 91.2 nanometers, and it's called the Lyman limit. As light from a very distant galaxy travels through space, it redshifts. Therefore, the Lyman limit, which is normally in the ultraviolet, also shifts towards the red. If a galaxy is completely invisible when viewed with Hubble's ultraviolet filter, F300W, but suddenly appears brightly in the blue, F450W, and other longer wavelength filters, it means that the galaxy's Lyman limit has redshifted just enough to fall between these two filters. This gives us the galaxy's redshift value, and thus its distance and age, with incredible precision. This was a revolutionary method that allowed for quick and effective distance estimation by simply comparing the brightness in a few different filters, instead of performing hours-long observations to measure a galaxy's full spectrum. Thanks to this method, scientists were able to quickly classify the thousands of galaxies in the Hubble Deep Field. But this classification brought forth a new problem: data processing. The 342 separate exposures collected over 10 days amounted to tens of thousands of gigabytes of raw data. Each image was contaminated with cosmic rays, hot pixels, satellite trails, and countless other sources of noise. Cleaning and combining this data by hand would have taken years. It was at this point that automated data processing software, or what called pipelines, came into play. Scientists at the Space Telescope Science Institute developed a special software package to process this massive dataset. This software worked like an assembly line in a car factory. Raw data went in one end of the line, passed through a series of standard steps, and came out the other end as a cleaned, calibrated product ready for scientific analysis. These steps included flat fielding to correct for the unique sensitivity differences of each CCD chip, dark current subtraction to remove the sensor's internal noise, and complex algorithms that combined the dithering data we mentioned earlier. This automated process not only saved time, but also ensured that the results were repeatable and objective. It prevented different scientists from reaching different conclusions using the same data. This pipeline approach was so successful that it has now become a standard procedure for all major astronomy projects, mehr's, including James Webb. The HDF changed not only the universe, but also the way we do astronomy. So, what did the scientists do when all this data was processed and the distance, shape, and brightness of thousands of galaxies were measured? The answer was perhaps the most revolutionary aspect of the project. They opened the data to everyone. Normally, a team that wins such valuable observation time would keep the data to themselves for years, publishing the most important discoveries first. But Robert Williams chose a different path. As soon as the data calibration was finished, he released all the raw and processed images through a public archive accessible to all astronomers worldwide. This was an unprecedented decision. It was the beginning of the open science era. Thanks to this decision, hundreds, thousands of scientists from all over the world began to analyze the HDF data according to their own areas of expertise. Some searched for the most distant galaxies, while others studied galaxy mergers. Some calculated star formation rates, while others searched for supernova explosions. The HDF image became the common property of all humanity, not just one research team. From this single observation, thousands of scientific papers have been produced to date. This is one of the most productive results ever obtained from any scientific experiment in history. But Williams's decision was a philosophical revolution that proved that knowledge multiplies by sharing and that the greatest discoveries are made through a collective effort. When these techniques and approaches came together, the Hubble Deep Field became more than just an image. It became a multi-layered scientific instrument designed to solve the deepest secrets of the universe. Strategic targeting, flawless pointing, ingenious data cleaning, clever distance measurement, and a revolutionary data sharing policy all came together to find a treasure in the middle of nowhere. But, so the most exciting part was not what we found in this treasure. The most exciting part was where this treasure led us, is because every single galaxy Hubble found, at every single redshifted point of light, pointed to a much larger, much darker secret about the future of the universe. This secret was the harbinger of a discovery that would shake the foundations of physics, showing that the universe was not only expanding, but accelerating. Now, the time has come to move towards the deepest, most fundamental reality that the Hubble Deep Field showed us, the findings about the ultimate fate of the universe, because in that tiny area the size of a grain of sand, the first clues about how the universe will end were hidden. And those clues were the harbingers of an earthquake that would shake not just astronomy, but physics itself to its core. Everything we've discussed so far was just the beginning of this grand epic. Now we come to the climax, because the things Hubble found by looking into that nothingness redefined humanity's place in the universe. It shattered theories, and it left us face to face with a reality so vast and strange that we could not have imagined it. Fasten your seatbelts, because now the tempo is going to maximum, and the universe's greatest secrets are being revealed one by one. The first tremor, the greatest census in history. Before the Hubble Deep Field, astronomers estimated there were about 10 to 20 billion galaxies in the observable universe. Even that was an unimaginable number. But HDF demolished that number. In that tiny spot, in that area the size of a grain of sand, more than 3,000 galaxies were found. This was 20 times more than expected. Scientists did a simple calculation. If every corner of the sky is this dense, then there must be at least 200 billion galaxies in the universe. In fact, later observations revealed this number could be as high as 2 trillion. This was the biggest inventory update in history. The universe was 100 times more crowded than we thought. But that wasn't the real shock. The real shock was that this discovery proved the cosmological principle. This principle states that the universe, on a large enough scale, looks the same in every direction. HDF confirmed this theory in a shattering way. In other words, Earth, the Milky Way, had no special place in the universe. Wherever we looked, we would encounter this carnival of galaxies. This was the final and greatest link in the Copernican revolution. We were not at the center of the solar system. We were not at the center of the galaxy. We were not special anywhere in the universe. This discovery had the effect of a bomb in the scientific world. Papers, conferences followed one after another. Humanity's cosmic address was instantly transformed from a quiet town in a remote corner to an ordinary street in a giant city with trillions of metropolises. This was a psychological revolution. The fingerprint left by the expansion of the universe was waiting to be deciphered. And the name of this code was the Lyman break technique. But it's better known as the disappearing galaxy trick. Because This method measures a galaxy's distance not by looking at where it appears, but by where it doesn't appear. To understand this, imagine you are looking out through a series of windows covered with different colored glass. You look through blue glass is shone, green glass, that's a Kopfer, and red glass. If a very distant car is not visible through the blue glass, but is clearly visible through the green and red glass, this gives you an important clue about the car's color. The Lyman break technique does exactly this. In the early universe, galaxies were surrounded by a dense fog of neutral hydrogen gas. This hydrogen fog completely absorbs light below a certain wavelength, especially ultraviolet light, just like a sponge absorbs water. The exact wavelength at which this absorption occurs is 91.2 nanometers, and it's called the Lyman limit, as light from a very distant galaxy travels through space. It redshifts. Therefore, the Lyman limit, which is normally in the ultraviolet, also shifts towards the red. If a galaxy is completely invisible when viewed with Hubble's ultraviolet filter, F300W, but suddenly appears brightly in the blue, F450W, and other longer wavelength filters, it means that the galaxy's Lyman limit has redshifted just enough to fall between these two filters. This gives us the galaxy's redshift value, and thus its distance and age. With incredible precision, this was a revolutionary method that allowed for quick and effective distance estimation by simply comparing the brightness in a few different filters, instead of performing hours-long observations to measure a galaxy's full spectrum. Thanks to this method, scientists were able to quickly classify the thousands of galaxies in the Hubble Deep Field. But this classification brought forth a new problem: data processing. The 342 separate exposures collected over 10 days amounted to tens of thousands of gigabytes of raw data. Each image was contaminated with cosmic rays, hot pixels, satellite trails, and countless other sources of noise. Cleaning and combining this data by hand would have taken years. It was at this point that automated data processing software, or what called pipelines, came into play. Scientists at the Space Telescope Science Institute developed a special software package to process this massive dataset. This software worked like an assembly line in a car factory. Raw data went in one end of the line, passed through a series of standard steps, and came out the other end as a cleaned, calibrated product ready for scientific analysis. These steps included flat fielding to correct for the unique sensitivity differences of each CCD chip, dark current subtraction to remove the sensor's internal noise, and complex algorithms that combined the dithering data we mentioned earlier. This automated process not only saved time, but also ensured that the results were repeatable and objective. It prevented different scientists from reaching different conclusions using the same data. This pipeline approach was so successful that it has now become a standard procedure for all major astronomy projects, including James Webb. The HDF changed not only the universe, but also the way we do astronomy. So, what did the scientists do when all this data was processed and the distance, shape, and brightness of thousands of galaxies were measured? The answer was perhaps the most revolutionary aspect of the project. They opened the data to everyone. Normally, a team that wins such valuable observation time would keep the data to themselves for years, publishing the most important discoveries first. But Robert Williams chose a different path. As soon as the data calibration was finished, he released all the raw and processed images through a public archive accessible to all astronomers worldwide. This was an unprecedented decision. It was the beginning of the open science era. Thanks to this decision, hundreds, and thousands of scientists from all over the world began to analyze the HDF data according to their own areas of expertise. Some searched for the most distant galaxies, while others studied galaxy mergers. Some calculated star formation rates, while others searched for supernova explosions. The HDF image became the common property of all humanity, not just one research team. From this single observation, thousands of scientific papers have been produced to date. This is one of the most productive results ever obtained from any scientific experiment in history. But Williams's decision was a philosophical revolution that proved that knowledge multiplies by sharing and that the greatest discoveries are made through a collective effort. When these techniques and approaches came together, the Hubble Deep Field became more than just an image. It became a multi-layered scientific instrument designed to solve the deepest secrets of the universe. Strategic targeting, flawless pointing, ingenious data cleaning, clever distance measurement, and a revolutionary data sharing policy all came together to find a treasure in the middle of nowhere. But, the most exciting part was not what we found in this treasure. The most exciting part was where this treasure led us, is because every single galaxy Hubble found, at every single redshifted point of light, pointed to a much larger, much darker secret about the future of the universe. This secret was the harbinger of a discovery that would shake the foundations of physics, showing that the universe was not only expanding, but accelerating. Now, the time has come to move towards the deepest, most fundamental reality that the Hubble Deep Field showed us. The findings about the ultimate fate of the universe, because in that tiny area the size of a grain of sand, the first clues about how the universe will end were hidden. And those clues were the harbingers of an earthquake that would shake not just astronomy, but physics itself to its core. Everything we've discussed so far was just the beginning of this grand epic. Now we come to the climax, because the things Hubble found by looking into that nothingness redefined humanity's place in the universe. It shattered theories, and it left us face to face with a reality so vast and strange that we could not have imagined it. Fasten your seatbelts, because now the tempo is going to maximum, and the universe's greatest secrets are being revealed one by one. The first tremor, the greatest census in history. Before the Hubble Deep Field, astronomers estimated there were about 10 to 20 billion galaxies in the observable universe. Even that was an unimaginable number. But HDF demolished that number. In that tiny spot, in that area the size of a grain of sand, more than 3,000 galaxies were found. This was 20 times more than expected. Scientists did a simple calculation. If every corner of the sky is this dense, then there must be at least 200 billion galaxies in the universe. In fact, later observations revealed this number could be as high as 2 trillion. This was the biggest inventory update in history. The universe was 100 times more crowded than we thought. But that wasn't the real shock. The real shock was that this discovery proved the cosmological principle. This principle states that the universe, on a large enough scale, looks the same in every direction. HDF confirmed this theory in a shattering way. In other words, Earth, the Milky Way, had no special place in the universe. Wherever we looked, we would encounter this carnival of galaxies. This was the final and greatest link in the Copernican revolution. We were not at the center of the solar system. We were not at the center of the galaxy. We were not special anywhere in the universe. This discovery had the effect of a bomb in the scientific world. Papers, conferences followed one after another. Humanity's cosmic address was instantly transformed from a quiet town in a remote corner to an ordinary street in a giant city with trillions of metropolises. This was a psychological revolution, but the earthquake was just beginning. The second earthquake's more violent wave came from the age of the galaxies. The universe had a biography, and Hubble managed to read the most exciting chapter of this biography, the cosmic noon. The overwhelming majority of galaxies in the HDF were an incredibly bright blue color. This was the sign of young, hot, and massive stars. These galaxies were producing stars as if they had gone mad. When scientists analyzed this data, they discovered the most productive period in the history of the universe, about 3 to 6 billion years after the Big Bang. In a period with a redshift value between 1 and 2, the universe was experiencing a star production explosion. A typical galaxy at that time was giving birth to stars 10, 20, some even 100 times faster than the Milky Way does today. This was the golden age of the universe, the moment when the universe was most energetic, brightest, most creative. This discovery completely changed galaxy evolution models. It was thought that galaxies grew slowly and steadily. But HDF showed the exact opposite. The youth of the universe was not a calm growth, but a violent and explosive adolescence. This revealed the Maddow diagram, a graph that summarizes the star formation history of the universe. And this graph became one of the cornerstones of modern cosmology. We had understood that the universe was once much more alive, and within that vitality lay our most personal, most profound secret, the third earthquake, our origin. After the Big Bang, there were only 3 elements in the universe: hydrogen, helium, and a little bit of lithium, the heavy elements that make us up, like carbon, oxygen, jets, and iron, did not exist. These elements could only be forged in the nuclear furnaces at the hearts of stars and scattered into space by supernova explosions. So, for the elements necessary for life to exist, at least one generation of stars had to live and die. Astronomers expected the oldest galaxies to be metal poor for this reason. But HDF shocked them again, even in the most distant, oldest galaxies in the image, jetschients. There were surprising traces of carbon and oxygen in their light spectra. How was this possible? This showed that the chemical enrichment process of the universe was much faster and more violent than previously thought. The first generation of stars, the population 3 stars, were, according to theories, incredibly hot and short-lived monsters, hundreds of times more massive than the Sun. They must have lived for only a few million years and died in massive explosions. And these explosions polluted the universe with heavy elements so quickly that the seeds of life were sown billions of years before we were born. What HDF showed us was not just distant galaxies. It was the first, heart's most violent moments of the cosmic forge, where the atoms that make up our bodies were forged. We are, quite literally, the children of those explosions from 12 billion years ago. This discovery turned the phrase, "we are stardust," from a poetic expression into an observable scientific fact. Yet, the biggest earthquake, that final tremor that changed everything, came at the end, HDF had shown how full the universe was, how fast it evolved, and our origins. But it also contained the first and most frightening clue to the ultimate fate of the universe. The redshift data from the galaxies in the HDF had proven that the universe was expanding. But when this data was combined with later observations of Type 1, a supernovae, an unbelievably truth emerged. The universe was not just expanding, its expansion was accelerating. This was against all the laws of physics. Gravity should have slowed the universe down, perhaps one day causing it to collapse back in on itself, the Big Crunch. But the exact opposite was happening. There was a mysterious, invisible energy pushing the universe apart, driving everything away from everything else. This energy was named dark energy. And when this discovery was announced to the scientific world in 1998, it was crowned with a Nobel Prize. This was the resurrection of the cosmological constant, lambda, which Einstein had once added to his equations and then called his biggest blunder. The precise distance measurements provided by HDF had laid the groundwork for this revolutionary discovery. This finding also told us what the end of the universe would be. There would be no Big Crunch. Instead, there would be a big freeze or heat death. Galaxies would recede from each other at an ever-increasing speed, eventually disappearing from view. The universe was heading at full speed towards a cold, hot-chocked, dark, whole, and absolute void. The vibrant galaxy party that HDF showed us was in fact the universe's most beautiful but final party. We were witnessing the last moments of that party, as these discoveries came one after another. Scientists wanted to look even deeper. The success of HDF led to the Hubble Ultra Deep Field, HUDF, and Hubble Extreme Deep Field, XDF projects. The HUDF bull in 2004, with an even more sensitive camera than HDF, observed for 11 days and found galaxies from just 400 to 800 million years after the Big Bang. But the record was set in 2012. The XDF combined all of Hubble's observations of the same spot over 10 years. A total exposure time of 2 million seconds, or 23 days. And the result, galaxies from 13.2 billion years ago, when the universe was only 500 million years old, and every deeper look confirmed the same terrifying and magnificent truth. The universe was filled with galaxies much earlier than we thought. And now it was rapidly expanding into an endless darkness. All these discoveries, the numbers, the shapes, the stars, the elements, and the inevitable end of the universe, all were hidden in that daring 10-day gamble. In a place where there should have been nothing. The entire story of the universe was written. But what did this story mean for us? What did these mind-boggling facts mean for us as humanity? About our place in this vast cosmos? Because behind this scientific revolution lies a much deeper, much more philosophical question. It was waiting, and this question transcends the boundaries of science and enters the realm of philosophy, just because the meaning of these discoveries for us is much deeper than numbers. This is a moment of enlightenment that fundamentally changes humanity's relationship with the universe. Each pixel of the HDF is not just a scientific data point, but also serves as a cosmic mirror, and what we see in that mirror is simultaneously astonishing, terrifying, and incredibly hopeful. Therefore, now we will examine what this scientific revolution means for humanity, its most epic consequences, and the greatest legacy it has left behind. Because this story is not just about galaxies, it is also our story. And the first epic meaning was this: the universe became ready for life much earlier than we could have imagined. Pre-HDF theories predicted that it would take billions of years for the heavy elements necessary for life to form. The first few billion years of the universe were seen as a primitive and sterile period. But Makha HDF shattered this picture. The abundance of carbon, Sattva oxygen, and other metals, even in the most distant, oldest galaxies in the image, showed that chemical enrichment occurred at an incredible speed. How was this possible? The answer lay hidden in that legendary first generation of stars called Population 3. These stars must have been formed from pure gas containing nothing but hydrogen and helium. Therefore, they were giants that could reach hundreds of times the mass of the Sun. And the more massive a star is, the shorter its life. These giants lived for only 1 to 2 million years. A cosmic blink of an eye, and died in massive hypernova explosions. These explosions were 100 times more powerful than a normal supernova, and in the process, they scattered tons of heavy elements they produced in their cores to every corner of the universe. What HDF showed us was that the universe, when it was still a baby, just a few 100 million years after the Big Bang, already had all the raw materials necessary for life. This pushed the timeline for the beginning of life in the universe back by billions of years. The scientific world was shaken by this finding. The field of astrobiology was reborn. Because the question was no longer, is there life in the universe, but how early did life begin? But this early start revealed another secret of the universe. The second epic meaning, the Dark Ages, were much shorter than we thought. For about 380,000 years after the Big Bang, the universe was a hot soup of plasma. Then it cooled and became covered in a fog of neutral hydrogen gas. This was a period when light could not travel freely, when the universe was completely dark. Astronomers thought these dark ages lasted for about 1 billion years. It would take time for the first stars and galaxies to form within this fog, and for the light they emitted to dissipate this fog, the Reionization. But for HDF destroyed this theory as well. Even the most distant galaxies in the image, when the universe was only 800 million years old, showed that the Reionization process was almost complete. This curtain of fog had been lifted much earlier than expected. How was this possible? The answer, again, lay in the incredible power of those first galaxies. The small, irregular clumps of galaxies in the HDF contained so many young hot stars and were so dense that the ultraviolet radiation they emitted burned away the universe's fog like a flamethrower. In just a few 100 million years, they transformed the universe from a dark and opaque place into the transparent and light-filled place we know today. This was the most dramatic transformation in the history of the universe, and HDF allowed us to witness the final moments of this transformation. This finding threw early galaxy formation models into the trash, because galaxies were not supposed to be this early and this powerful. This implied that the dark matter halos, the building blocks of the universe, were gathering gas and turning it into stars much faster than previously thought. And this speed gave rise to the third epic meaning. The future of the universe was even more shocking than its past. The precise distance measurements provided by HDF paved the way for the 1998 discovery of accelerating expansion, one of the greatest discoveries in human history. This showed that the universe was not just expanding, but that this expansion was accelerating. This discovery was so shocking that Albert Einstein himself would not have believed it, because gravity should have pulled everything towards everything else. But there was a repulsive force in the universe that opposed, and even overcame, gravity, dark energy. This energy was a property of space itself and was present in every cubic centimeter of the void. And as space expanded, more void was created, and thus this repulsive force increased. This was a kind of cosmic runaway reaction. This discovery revealed that 68% of the universe is made of this mysterious dark energy, 27% of dark matter, and only 5% of the normal matter we know. In other words, the thousands of galaxies and trillions of stars we see when we look at the HDF are just a tiny foam on the universe. The real ocean was dark and invisible. This was the biggest crisis in modern physics, because we had no idea what dark energy was. But we knew it existed, because we could see the universe accelerating towards its own end. All these discoveries led to the fourth and perhaps most important epic meaning. The very nature of science changed. Robert Williams' decision to open the HDF data to the whole world as soon as the analysis was finished created a revolution in science. This was the beginning of data democracy. This bold decision declared that knowledge was not the property of a select few, but the common heritage of all humanity. From this single dataset, thousands of papers have been written by more than 10,000 scientists to date. This was the highest efficiency rate ever obtained from any scientific facility in history. This open science model became the standard after HDF. All major projects, including Hubble's successor, the James Webb Space Telescope, now share their data through public archives. This has exponentially increased the speed and efficiency of science, because now brains from all over the world could work together on the same problems. The legacy of HDF is not just the galaxies it found, but the fact that it forever changed the way we find and understand those galaxies. It was a triumph of humanity's collective intelligence and a belief in the power of collaboration. All these epic discoveries, a universe ready for life early on, dark ages much shorter than expected, a cosmos accelerating towards its own end, and a data revolution that transformed science itself, all came from that tiny, dark spot in the sky. But now, after this dizzying pace, it's time to pause and think. What do all these facts, these mind-boggling numbers and theories, mean for us? For those of us living on that tiny, pale blue dot within this vast cosmos? Because the deepest impact of these discoveries is felt not in the lenses of telescopes, but in our minds and hearts. This is an invitation to rethink our relationship with the universe. And this invitation leads us to the most philosophical questions of science. It takes us there. And now we ask ourselves that most fundamental, most human question. What does all this mean for us? In the midst of these mind-boggling discoveries, who are we? It's time to stop accelerating and slow down. Time to pause and reflect, because the greatest gift the Hubble Deep Field has offered us is not just scientific data, but the opportunity to face ourselves in the mirror of the universe. This mirror is a ruthless and compassionate surface that shows us both how insignificant we are and how miraculous we are at the same time. Therefore, let us now seek our own place within these cosmic paradoxes. The first and greatest paradox concerns our size. It, on one hand, there is an unimaginably large universe, spanning 93 billion light-years and containing trillions of galaxies. On the other hand, there is you, a conscious being about 1.7 meters tall, less than a speck of dust within this universe. How can such a tiny part of such a colossal structure think about the structure itself? This is one of the most tragic truths Hubble has presented us. The most distant galaxy we see is 13 billion light-years away from us. Its light has only just reached us. We cannot even dream of going there. The laws of physics say that we are inhabitants of a small island, trapped in this cosmic ocean. While it would take us thousands of years to reach even neighboring star systems, those galaxies are forever an unattainable dream for us. This creates a deep sense of cosmic loneliness and insignificance. We are merely spectators in this vast theatre, sitting in a very distant seat, who can never get on stage. But right at this point, a magnificent beauty now is born from that tragedy. Yes, we are physically small and limited, but our minds are limitless. Our bodies may be chained to Earth, but our consciousness, thanks to Hubble's eyes, can travel back 13 billion years. Even if we cannot touch those galaxies, we can understand them. We can calculate how they were born, how they evolved, and what will happen in the future. You, too, are at the very center of this incredible contradiction. Your physical existence may be nothing compared to the universe, but your consciousness, which tries to understand that universe, asks questions about it, and seeks answers, may be the rarest and most precious thing in this universe. This shows that our smallness is not a curse, but a blessing, because our effort to understand something so large despite being so small is the most fundamental act that gives meaning to our existence. The second paradox is about time. On one hand, there is an almost eternal universe with a colossal past of 13.8 billion years and a future of perhaps trillions of years ahead of it. On the other hand, there is a human life of an average of 80 years, which flashes and fades in an instant in this infinite ocean of time. On the universe's calendar, all of human history is less than a second. Your existence is but a vibration within that second. This is a tragic fact that shows how temporary and fragile our existence is. The galaxies Hubble saw existed billions of years before we were born, and will continue to exist billions of years after we die. Faced with this overwhelming scale of time, our own lives, our efforts, our joys, and our sorrows may seem meaningless. We are like drops of water that appear for a moment in this cosmic river and instantly disappear. This thought can create a feeling of nothingness and despair. But, again, a miracle is born from this tragedy. Yes, our time is limited, but it is precisely this limitation that makes that time valuable. The universe may have infinite time, but it has no consciousness to experience this time. We, on the other hand, have only a brief moment. But that moment is filled with consciousness. In that brief moment, we can fall in love, create art or just learn new things, and think about the universe itself. You are that brief but precious moment. At the end of a 13.8 billion year history, you came into existence as a part of this universe that can think about itself. This is an incredible privilege. Perhaps the greatest purpose of the universe's billions of years of existence is for conscious beings like you to emerge in those brief moments and bear witness to the beauty and mystery of the universe. Therefore, the scarcity of our time is not a tragedy. but rather the strongest motivation to live that time to the fullest. The third and most poignant paradox is between loneliness and togetherness. On one hand, there is a universe that is accelerating its expansion, forever tearing its galaxies apart from each other. A dark energy is pushing everything apart. In the future, all galaxies outside the Milky Way will disappear from view, and we, or those who come after us, will live in a completely isolated island universe. This is a picture of ultimate cosmic separation and loneliness. Each galaxy in the HDF is, in fact, mugshi, a neighbor, bidding us farewell. Even if we wave at each other, the distance between us is constantly increasing. This is a sad truth that suggests the most fundamental nature of the universe is separation. Everything is doomed to be torn apart in the end. But the exact opposite of this cosmic loneliness lies in our own existence. While those galaxies are moving away from each other, we are here, on Earth, connected to each other. We were born from the ashes of the first stars that HDF showed us, and every single carbon atom in your body was forged in the heart of a star that exploded billions of years ago. And that atom may have come from the same star as an oxygen atom in the body of the person sitting next to you right now. We are, quite literally, Maut's cosmic siblings. While the universe tries to tear us apart, our origin unites us. You, Art, are a part of this deep connection. You are connected not only to your own family or society, but also to that first explosion 13.8 billion years ago, and to everything that was born from that explosion. Looking at that image from Hubble is actually like looking at a giant family photo. Every point of light there is a distant relative. This is the greatest irony of the universe. No matter how great the forces that separate us, the origin that unites us is much deeper and much older. These paradoxes, being colossal yet understandable, being temporary yet conscious, being connected to each other in a lonely, expanding universe. These are the philosophical questions Hubble asks us, and there are no definitive answers to these questions. There are only personal journeys. But we are not alone on this journey, because these discoveries remind us of another truth, and that is, no matter how helpless we are in the face of this huge mystery, how powerful we can be when we come together. Because there is another secret behind that 10-day observation, and this secret is humanity's greatest hope. It is, and this secret is hidden in our fourth and final paradox, the dance of ignorance and knowledge. On one hand, thanks to the Hubble Deep Field, we know more about the universe than ever before. We can measure the age, size, content, history, and future of the universe with incredible precision. We can now see just a few 100 million years after the Big Bang, witnessing the birth of the first galaxies. This is the greatest accumulation of knowledge in human history. We are at a point in solving the secrets of the universe that our ancestors could not even dream of. This is an absolute triumph of human intelligence and curiosity. But, on the other hand, every new door this knowledge opens leads us into much larger and darker corridors. This is how every new thing we discover slaps us in the face with how much we don't know. HDF showed us thousands of galaxies. But we still don't know what the dark matter that holds those galaxies together is. It proved that the universe is expanding rapidly. But we have no idea about the nature of the dark energy that causes this expansion. It showed how early the first galaxies formed. But we still haven't directly seen those first single stars. The population 3 stars. As our knowledge increases, like us, the ocean of our ignorance expands in proportion. This is a tragic fact. The more we learn, the better we understand how little we know. Every answer brings with it 10 new questions. This is an endless quest that means we can never reach the peak of knowledge. But it is this very endless quest that is the beauty of science and human curiosity. If one day we knew everything, if all mysteries were solved, what would be left to be curious about? What new puzzle would excite us when we woke up in the morning to ponder over? Is our ignorance is not a weakness, but our greatest driving force. It is the fuel that pushes us to look deeper, to build bigger telescopes, to produce bolder theories. You are a part of this endless quest. Every book you read, every question you ask, every new piece of information you learn is a small drop in that great ocean. But without those drops, the ocean cannot exist. The accumulation of human knowledge has been formed by the accumulation of those small drops from millions of curious people like you. Therefore, instead of fearing the things we don't know, we should approach them with excitement, because they are the greatest proof that the adventure continues. These lessons that Hubble taught us are a cosmic coming-of-age story for humanity. We were once arrogant children who thought we were at the center of the universe. Now, we are transforming into adults who understand how small, how temporary, and how ignorant we are, but who are not afraid to face these truths. This telescope taught us not only about galaxies, but also humility. The decision of Robert Williams and his team to look at that empty spot for 10 days was in fact a form of intellectual humility. It was the bravest way of saying, we admit we don't know, but we are determined to learn. Without their courage, we might still be stuck in that old paradigm, believing that the universe is largely empty. But they chose to go after the unknown, and that choice changed everything. The success of the Hubble Deep Field proved to us this: the greatest discoveries are made not when we repeatedly confirm what we already know, but when we courageously pursue what we don't know, what we even doubt the existence of. This is a lesson that applies not only to science, but to life itself. When we show the courage to look into our own personal deep fields, our fears, our prejudices, and our unknown aspects, we can make the most surprising discoveries about ourselves. Because the greatest treasures are often hidden in the darkest and most empty-looking places. Therefore, the legacy of Hubble is not only scientific, but also spiritual. It reminds us of the virtue of wondering, of asking questions, and of admitting what we don't know. This is the most fundamental and beautiful aspect of being human. As we come to the end of this 10-day epic journey, we now know. We now know that the darkness in the sky is not due to emptiness, but to abundance. There are so many galaxies that most of their light has not yet reached us, or has been forever pushed away from us by the ruthless thrust of dark energy. We now know that we are temporary guests of this universe, but also its memory and consciousness. And most importantly, we now know that the greatest discoveries await us in the most unexpected places. Robert Williams's bold gamble expanded humanity's horizons forever. It paved the way for more powerful telescopes like James Webb and ignited a never-ending desire for discovery that takes us ever deeper, ever closer to the beginning of time. That 10-day recording is not just an image, but also a source of inspiration left for future generations. It is proof that even seemingly impossible things can be overcome with enough curiosity, courage, and collaboration, our journey ends here. But the story of the universe will never end, and the task of writing the new chapters of that story now rests with us. Because that whisper from 12 billion years ago is still ringing in our ears, and it tells us one thing: keep looking. In this video, we saw the birth of the universe after the Big Bang. But I didn't tell you a secret. What if the Big Bang wasn't a beginning? What if our universe is a phoenix, born from the ashes of a previous universe? On our next journey, we will look beyond the beginning of time to what happened before the Big Bang. Are you ready?